All right, thanks everyone for attending this talk. Thanks to the organizers. I am Max and working for Inno Switzerland, which is a startup here in Switzerland, with the mission to leverage data-driven approaches to reduce the carbon footprint of real estate assets. So that is buildings. And I would like to talk to you about one of my favorite use cases of machine learning in our company that really lies at the core of our business model, and I think it's very interesting. But before that, a bit of context. So in Switzerland, 30% of the greenhouse gas emissions are actually originating from building operations, and it is quite clear that any plan to mitigate climate change, we need to see this reduce a lot and as soon as possible. And this is there's a number of people working on the subject, and the main approach and the most usual approach is actually through refurbishment work, which is very effective, but also extremely slow and quite cost intensive. So we're trying to tackle this challenge, and we are doing so with a technology that we have developed that enables us to interface with any building and its heating system. So really very complex, modern, digital one, but also very old, legacy, analog ones, and generate data about the way the building operates. After some time of observation, we're able to actually go to phase 2, which is optimization, where we cross-reference this data, the data about the building itself, with weather forecast. And here we are not using a graph neural network to get that, but we purchased this weather forecast to basically control the heating system and reduce the energy consumption while guaranteeing the thermal comfort for the building users. So that is our main service. There's a number of nice feats. First of all, it's quite fast because we basically need 2 months worth of training data basically before starting optimization, which is a lot shorter than replacing anything on the building. And we observe energy consumption reduction from 10 to 35%, which is quite impressive, again, without changing a single brick or window on the building. And we have a very powerful pay-as-you-save business model. So that means that our service is financed by a fraction of the actual cost savings that it generates. And this is actually what I would like to talk to you and to present today. So to do that, we are relying on international standard that is maintained by the Efficiency Valuation Organization, and that works as follows. So we basically compare the baseline energy consumption for a given period of time, which is the energy that the building would have consumed had we not optimized it, with the actual energy consumption, the one we have affected by our optimization service. Then the difference between those two figures, that's the energy savings, and through the cost of energy that is climbing rapidly currently, we get the cost savings, and a fraction of that is actually what we invoice our clients. Now, the actual energy consumption, this is something we measure, so we have meters in place to measure this. But the baseline energy consumption is something that we have to model. And this is basically where we use machine learning to do that. So basically doing some regression on the energy consumption as predicted by some features that do not, and this is important, that are not impacted by optimization service. And this comes with a number of constraints. First, the model is used for invoicing, which means that we have to be very transparent in the way we compute this. So those deep transformer networks are pretty much out of the picture. Second, every building has basically its own dynamics, and we basically need one model per building, which means that we are not really building a model per se, but a model building pipeline that need to be automatized and that cannot be fine-tuned. Then, I mean, buildings data is messy. We often see anomalies, being breakdowns, some interventions on site, and we basically need a model that is quite robust against those. And finally, while we are observing the building to generate this training data, we cannot optimize. So we cannot make energy savings. And in our case, that also means we are not making money. So it is very important that we use a data-efficient model, and we don't have to wait 5 years to have the most precise and complex neural network to get the data for us, or the prediction for us. Now, as I said, there are a number of features we cannot use, and those are all the ones that we actually impacting by the optimization service, and this includes all of the measurements or most of the measurements that we make in the building. But we do use the features that do impact do impact the measurements or the consumption rather. And this starts with a very easy one, which is whether the building is being heated or not. And it sounds trivial, but actually getting that in a robust fashion is not so easy. Because at some point in time, by the end of the heating season, somebody will manually shut down the heating system, and the only consumption that will remain is that of domestic hot water, which has a very different dynamics. And then there is basically climate information that, of course, has a very strong impact, most of which comes from the outdoor temperature. Also have solar irradiance, wind speed, direction, and rain volume. So this is what the data that we are trying to predict looks like. So this is daily energy consumption of a building, relatively small one here, as a function of the outdoor temperature. And we see a clearly downward trend. And at some point it plateaus, and this is because at some point it's summer and then we don't heat anymore. And we see that in between those 15 and 20 degrees range, there is a bit of both behavior. We have some points that do not depend on temperature and some other that do. And this is the point that I was making. At some point somebody manually shut down the heating system, and then it's not correlated with outdoor temperature anymore. So we see that the outdoor temperature is able to explain quite a lot in a not so linear fashion, but still explain quite a lot of the signal. But we see that still there is quite some variance, right? So we do need those extra features to actually get better prediction. And this is basically what we get when we have a model that is fitted. So we see here between October and December is our baseline period. So this is where the building is basically operating on its own, and we're just measuring the consumption of the building. And at some point, 1st of December, we activate the optimization service, and the line basically split in two. There is this green one, which is the one that we measure, that is affected by the optimization service. And then there is the output of our model, which is the white one, which represents the consumption of the building had we not optimized it. So this shaded area then is the energy savings that we were able to generate. And this is computed then in a real-time fashion, which in this industry means daily, but it's not an annual computation. And we see some figures that are quite interesting. For instance, as we go towards the end of the heating season and we get a lot more solar power, then the energy savings are increasing a lot. So I think that this use case is very interesting because here it is applied to buildings' energy efficiency, but it can really be applied to any kind of energy efficiency and is not really related to the building aspect of it. There is a bit of constraint though. It needs, you need to have data to fit that, of course, and in some cases it's not so easy to get. And also, you need a consumption that is somewhat productive. You need to be able to reach the kind of accuracies that are much better than the energy savings that you are making, because otherwise the whole computation doesn't really make sense. Thank you for your attention, and you may not ask questions as there will be a panel discussion. Thank you.